Welcome to our workshop, everyone. Today, we're going to show you all the tools and techniques which you can use to supercharge your machine learning lifecycle from R&D to production. We're going to start our session with a brief introduction. We'll then talk about the machine learning lifecycle. And afterwards, we're going to move to the second and third parts of this workshop, where we show you how you can supercharge various components of your machine learning workflow, like experimentation component or model deployment, with a few exciting demos. And we will end the workshop with a Q&A session. So let's get it started. Who are we? If you haven't recognized me from the slide yet, my name is Azin Asgarian. I'm an applied research scientist at Georgian's R&D team, and I'm here today with two of our amazing machine learning engineers, Truskovskyi and Kyryl Truskovskyi. So what do we do at Georgian? We invest in the best so at Georgian, we invest in the best growth stage AI companies like ClickUp, and we do this by taking a data-driven approach. This includes using data and AI to identify the best companies for investment, as well as supporting our portfolio companies post-investment. For example, our team is building a platform to help our portfolio companies to overcome the scaling challenges. And now you may ask, why does an investment company need an R&D team for, which I think is an excellent question. So the short answer is driving product differentiation. We help our portfolio companies to identify the disruptive tech trends ahead of the market, to hire the best talent for their team, to understand the impact of various variables on business software models, and lastly, and most importantly, to adopt the differentiating technology trends and overcome their technical challenges. And we do this basically by collaborating with them in different shapes and forms. Sometimes we play an advisory role. In some cases, if the problem is well scoped and niche, we try to solve it in a hackathon, which can take from a few days up to a few weeks. And in some cases, if the problem requires more in-depth research, we run a deep engagement with our companies, which can take from a few months up to a year. And we try to share our findings and work with the research community by creating reusable toolkits or publishing our research in AI conferences and workshops. So if you're interested to learn more, please check the QR code below this screen. And as I said, we work with a lot of companies. We have more than 40 companies in our portfolio, companies like ClickUp, Tractable, Spins, and these companies are moving with a very fast pace. So for us, in order to have the maximum possible impact and help our portfolio companies as much as possible, we have to be very efficient. And at the same time, we have to constantly update ourselves to stay out of the technology trends. So in the rest of this workshop, we're going to show you how basically we implement this idea when it comes to the machine learning projects. So let's start the first part of this workshop, machine learning lifecycle. I love this analogy from Casey Kozyrkov, chief decision scientist at Google, that says machine learning research is like baking cookies and machine learning in industry is like running a bakery. So with having this analogy in mind, what we wanted to talk today is basically how we can run a bakery efficiently today. So a bakery, like any other system, has its own components. And in order to make the whole system efficient, we have to learn about different components and how we can make them efficient separately. So let's start with that. Let's see what are these components that we're talking about. The first and probably the most component in the machine learning lifecycle is data. The data that you collect, the way you process it and manage it, has a huge impact on the performance of your machine learning model. Similar to how you would end with tasteless cookies if you use pretty bad ingredients, your machine learning models would perform poorly if you train it on data that is managed poorly. So after we collect our data, or after we have our ingredients in hand, the next step is experimenting with different ideas and recipes to find the best one. And once we find the best recipe, it's time for baking the cookies. And with having the cookies in hand, we can go around and distribute our cookies to our customer. And then we'll start the monitoring this stage, and we'll aim to get some feedback from our customers to see how our cookies are tasting. And by any chance, if we have an unhappy customer, then we have to go back and either change our ingredients, get better ingredients, or change our recipe. And we'll have to do this over and over again till we reach 4.9 out of 5 Google star reviews. And this is how you can have a very successful bakery. But going back to the concept of machine learning, so now we know, different components of the machine learning lifecycle. And the next question is that now that we know these components, how can we make each of these components more efficient? And with that, I'll pass it to Chris to talk about the first two components, data and experiments.
Thank you very much, Azin. Well, let me share my screen. You guys can see my screen, right?
Yes.
All right, awesome. So yeah, thank you very much, Azin, for running us through an overview of the machine learning lifecycle. For my part of the talk, I'll focus on the two phases where data scientists spend most of their time in, the data and experiment phase. In the data phase, it encompasses a wide variety of operations from storage, access, labeling, all the way to processing and management of the data itself. There's a lot of things that we can talk in here, and it is beyond, like, we can cover all of it in just one short talk today. However, for today, I'd like to focus on one aspect which I think can help data scientists speed up their workflow when producing models, and that is data versioning. In other words, how did a model come about? Which data sets, which config files were used to train a model? I think this topic deserves a bit more attention than it currently receives. We currently have very well understanding of the importance in versioning our code and pinning our dependencies. This is all so that we can achieve a reproducible build and reproducible behavior when we need to debug our code. When it comes to machine learning, however, machine learning models are not just a function of the code, but also the data that's used to train it. And as such, I think we should place equal emphasis on versioning the data. And data versioning allows for faster model development, as it allows you to know what the inputs to your model are. As a data scientist runs more and more experiments, it becomes harder to keep track of which inputs, which data sets are used to train which models. And without having this knowledge of what goes to what, it becomes hard, if not impossible, to figure out why a particular model is performing poorly. Is it because of the code? There's some bug in the code, or is it something to do with the data set that we've received in that training process? Furthermore, this aspect is important as compliance and auditing becomes more front and center within our field. It is imperative that we are able to track the data sets that are used to produce a model before it goes into production so that we can audit it beforehand. Another reason why data versioning allows for faster model development is simply because it facilitates team collaboration. If every data scientist within a team is able to reproduce an experiment on any branch, this allows for tighter collaboration within the team. We are not bottlenecked necessarily by the one data scientist who only has access to the data set, or the only data scientist who has context to how a particular model was produced. Anyone can come in and collaborate in building that model. So in this talk, one tool that can help us to achieve data versioning is data version control, or DVC. There are two aspects which I think make DVC as a tool stand out. The first of which is, as the name implies, it helps to version control your data and models. And how it does it on a really high level is that DVC keeps track of the metadata of a particular file. And rather than committing the actual file into Git, it commits the metadata itself into Git, and therefore establishing a history of a particular data set with a particular commit. Meanwhile, the actual data itself is cached and stored in a remote storage like S3 or GCS, and this allows for easier sharing of particular data sets across the various teams. The second feature of data version control is DVC data pipelines. DVC data pipelines is like the glue that kind of like combines both code and data. It keeps track of all the steps that are required to reproduce a model, and this allows you to easily reproduce someone else's model. And we will cover more details on DVC and how we can use them later in our demo today. Next up, we have the experiment phase. In this phase, data scientists primarily spend their time training and validating various models. They may perform hyperparameter tuning. And when we have more and more experiments, then we start to do experiment tracking as well. As you can imagine, and in the experimentation phase, it is an inherently iterative process. To find a good model requires many iterations in terms of hypothesis testing, trying out different model architectures, and even hyperparameter tuning. As the trend moves towards larger data sets and larger models, training time will naturally become longer and longer, which effectively limits the number of iterations a team can perform before they put a model in production. And therefore, if you want to get better models to serve to our customers, in other words, better cookies, we need to cut down on training time. How may one go about doing that? The first thing that may come to mind is to spin up a Jupyter notebook and write the code in a Jupyter notebook. While this may be fast at first, it doesn't really scale as we want to scale out to many more experiments. Reasons being that, one, code in Jupyter notebooks are notoriously hard to reproduce because the codes themselves can be run out of order. Furthermore, a code that's written in Jupyter tends to not be modular enough, and this limits its reusability and how much we can debug it should something go wrong. In an ideal scenario, we want our training code base to be in such a way that it minimizes training time, such that we can use all the hardware accelerators present on a particular machine that we are training on. It should have minimal boilerplate, as boilerplate reduces, and it should have minimal boilerplate as this allows you to have a shorter development time, and it also minimizes the risk of introducing any pesky bugs. Furthermore, when we want to tweak our experiments, it should only involve, ideally, it should only involve a change to the config file and not necessarily, and we don't have to go and change our source code. Similarly, there shouldn't be a need to rewrite code should we need to push a model into production. So with that in mind, we can show you how we use PyTorch Lightning. So at Georgian, we perform multiple engagements with companies, and sometimes when we get to use PyTorch, we will use a secondary framework called PyTorch Lightning to speed up our experimentation velocity. What is PyTorch Lightning? It is a lightweight wrapper around PyTorch, and it helps to make your code more modular and therefore more scalable. I can kind of give you a very quick high-level overview of what the framework does. If you imagine over here to be your deep learning code, PyTorch Lightning first requires you to decouple your research code. And what is a research code? This includes things like model definitions, how you perform the forward pass, the optimizer that's used, and the loss function, for example. So in PyTorch Lightning, the code that's related to research is put aside into a Lightning module. Secondly, we would decouple the code that's related to data. So code that's related to data includes things like loading the model, loading the data sets and forming batches out of those data sets. Those logic can go into a different object called a Lightning data module. And what remains now typically is training boilerplate. This includes things that are like the for loop that's used to run the training, and it is not specific to any particular deep learning training use case. It's the same across all use cases, and therefore it would be ideal if we as users wouldn't have to rewrite things that are boilerplate, right? And so when you decouple your code into research and data code, and you may use PyTorch Lightning automatically out of the box, the boilerplate is taken care and abstracted away from you. And this includes certain things. Not only does it include the training and evaluation loops, but it also entails things like model checkpointing and early stopping, which helps with our training, our experimentation experience. Furthermore, by using PyTorch Lightning, we get a lot of very cool engineering features for free, such as multi-GPU and multi-node training, and automatic mixed precision training, and many, many more. So with that being said, we can move on to perhaps the start of our demo. And here I'll just preface by saying that, oh yeah, before we go to demo, if there's any questions, feel free to just go off mute or mention in the chat. Is there anything so far, Azin? Okay, cool. Yeah.
No, I don't think there is any question in the. Oh, there is one question from Akshay. What does multi GPU mean?
Multi-GPU. So when you train with PyTorch, if you were to write it yourself, you typically would set the device to use a GPU, but it will only use one GPU on the machine. Multi-GPU training means that you're able to use all the GPUs that are available on your machine to train at once. And to do so without using PyTorch Lightning is a really heavy engineering effort, as you need to significantly rewrite your code base. Yeah.
Okay,
All right.
there is one more question. So the speed here is particular to using certain framework, DVC, PyTorch Learning. Are there certain lean practices as well?
Lean practices.
I think probably practices that are agnostic, framework agnostic, or.
Right. So the way I would think of speed in this presentation is in two forms. One form comes in, taking advantage of all the hardware accelerators that are present. So that is more from a raw training speed perspective, but also from an experimentation experience. If you're able to very quickly check out a different branch and try out different experiments, then all of a sudden that also means that we can very quickly ramp up on new experiments and produce models just as quickly. Yeah. So in terms of other lean practices, I would just say things like, having unit tests and having a very well-developed CI/CD pipeline. All of these processes and general software development best practices all lend themselves well to our developing ML models too. All right, so let's go on to the demo. So to give you an idea of what we're going to do today, we're going to do a very simple exercise. We will be training a handwritten digit classifier on the MNIST dataset. So this is just a classifier that predicts between predicts on 10 classes, right? Whether a particular digit is 0, 1, 2, 3, all the way up to 9. We will be loading a pre-trained model and putting a new untrained layer at the top to perform the classification. We will start off with a very simple example in the Jupyter notebook, and then we'll show how we can use DVC to help version our data and to reproduce experiments, and when we get updated data. In the experiment side of things, we'll see how we can refactor our pure PyTorch training code into PyTorch Lightning. Not only that, we'll also use the latest features that came out recently in PyTorch Lightning to create a reusable CLI script that can perform not only training, but also evaluation and inference of our models. And we can see how we can use those same features to quickly generate a custom config so that you can train a model and just change things in your config as opposed to digging into the source code, because that is not so scalable. All right, with that being said, let's hop over to my IDE. Okay, so in this IDE, here you can see I have a Jupyter notebook. This might be what it looks like when you start training a new model for the very first time. You write things in Jupyter. We'll have things here like hyperparameters.
Oh, yes. Sorry for interrupting. Do you mind zooming in a little bit?
No problem.
Thank you.
Okay, I hope this is better.
Yeah, a lot better.
Okay, nice. So in here, we'll have things like, in a typical training scenario, you will have things like hyperparameters. In this case, they're built into the script, and ideally, they should be separated from the script in a config file, so it's easy to tweak things. We define devices over here. In this case, with whether to train on a CPU or on a GPU if a GPU is available. We have some code to load different types of models. In this simple example, I have just code to load a ResNet model or a MobileNet model. And once the model is loaded, it's then placed onto a particular device. So if you use this approach, you will only be able to place at most one model per device. And this is not as ideal if you have multiple GPUs that you want to train with, right? We'll show you more later. Since we are performing an image classification problem, we do have some pre-processing transforms here from Torch Vision to help us with pre-processing as well as data augmentation. Apart from that, we also have some code to load data, right? how do we get data, how do we load an image and a label for a particular index? And this is what it does here. So in this example, we have defined an MNIST data set to load training, validation, and test data. And for each of those data sets, there is a corresponding data loader in PyTorch. For those of you who are not familiar with what a data loader is, it is a PyTorch construct that is responsible for knowing how to form a batch given various examples from a data set. So in the training case, we want a batch to have a size of 32 and to shuffle them. Whereas for validation and test, you have a different size, and maybe we don't want to shuffle them because there's no need to shuffle those results. Finally, we also should define our criterion, which is our loss function, to optimize the model as well as the optimizer in itself. Now, once we have all these little components ready, we are ready to begin our training. We just need to write, here I've written a simple training and evaluation loop, a for loop across all the epochs, and then I loop across all the data within the training data loader. And every so often, I print out the loss at a particular point in the training, and then we can see the results over here. Now, this may not seem that bad, but it's also a pretty bare-bone example. If we need to if you want to add more functionality, say if you want to perform model checkpointing, mixed precision training, or even, let's see, early stopping, this code here can get complicated really, really quickly. And when that happens, and then we find a bug, it takes a long time. It might take a long time to debug what's going on. So, and this is some of the reasons. Apart from that, we also have to rewrite the code significantly if you want to utilize multiple GPUs to train. All these pain points slows down our iteration speed when we want to put out new models, right? So this is some of the, as you can see, and so with those things being said, we can show you how PyTorch Lightning helps to make our code cleaner, more cohesive, and more scalable for experimentation. So when we recall from those slides, the first thing we got to do is decouple the research code from everything else. And in my case, I've written it in model.py. Here, I've defined a class that inherits from Lightning module, and this is where all my research code sits. And here I've defined how my model should behave during training, validation, and testing. In all these cases, I made them to do the same thing. They are responsible in the training. For example, in the training phase, they go through a forward propagation step, and then we compute both the loss and metrics. And with those variables, we can then save them into a log file and use them later for experiment tracking. In this object, in this class, we've also defined optimizers that we want to use for training as well as the loss function. I've also included custom functions over here, which contains our model definitions. Next up, we have one little thing here as well is that I've also included transforms in here. These are the pre-processing and data augmentation objects that are part of Torch Vision. And by including them here, I can also enable them to take advantage of the GPUs when we want to train them. Yep. So the next thing from here, now that we've refactored our research code, the next thing to refactor is our data code. And we will put them in a data module. Here I've subclass a Lightning data module, and I've defined the data sets that I'll be using for this training, as well as the corresponding data loaders for train, validation, and test. So this is really similar to what we have just now, but perhaps one thing I can bring your attention to is that I've also specified some number of workers. And what this means is that when it comes to loading data, the data will be loaded in parallel by multiple workers in the CPU. That way, training itself is not bottlenecked, hopefully not bottlenecked by the data loading, but more in the forward and back propagation of the models themselves. So now that we've defined the Lightning module as well as the Lightning data module, it's time to put them all together for training. Typically in PyTorch Learning, you would create a trainer object and feed those two classes into it. But for the purposes of this demo, I'd like to share something that's a bit more cutting edge that came out quite recently, and that is the use of the Lightning CLI. as you can see, the amount of boilerplate here is almost to nothing. And what does the Lightning CLI do? Well, it allows you to use this one script to do not just training, but also inference and prediction, for example. And I can kind of just show it to you very quickly. Entry point, sorry. As you can see, in this few lines of code, we are able to do so many things already. And tune, test, feed, and so on. And so let's go specifically into fit, since we want to train the model, right? So one of the beauties of having a Lightning CLI is that you don't have to write your argument parser. The argument parser is out of the box for you already. And as you can see over here, it provides all the parameters and arguments that you can tweak and configure for your particular training process. Those are the ones from the trainer themselves. And not only that, you also have it automatically figures out the inputs that are required for your custom model and your dataset, which is pretty amazing. Having said that, it's not that fun and not that ideal as well to be specifying each one of these parameters in the command line. It's laborious and not reproducible. So one thing you can do is you can convert all your required arguments into a config file. And the way to do so is just to add, I think, print, maybe like this, print config, right? And then you can then save it to a YAML file, for example. So I've done that already, and this is what it looks like. So this contains all the possible knobs that we can tweak for our training. Perhaps some of the things I like to highlight over here is that with this config file, for example, we can choose to train on a CPU, on a GPU, maybe even a TPU, or we can just set it to auto. And then PyTorch Lightning will figure out what's the best approach for your, what is the best hardware available for your device. Similarly, you can set the number of devices you would like to use, or just set it to auto. And once again, it will figure out, PyTorch Lightning will figure it out for you. We've also defined some more, we also defined some checkpoints over here, how we want to do checkpointing, as well as where our data sets will be sitting in. I'm using a mobile net here just for the speed of the demo. All right, so now as you can see, with PyTorch Lightning, we've refactored our code out into very cohesive chunks of code. And we have now a config file that allows us to very quickly and very easily change things for different experiments. And the best part is we don't have to rewrite our code at all. So with that being said, before we jump into training, so if you want to train, I guess you would do something like this. You would say config, and then you provide the config file. But before we jump into training, maybe we'll take a step back and also see how we can take advantage of DVC for our demo, right? So
there's one question about the Lightning CLI. Maybe, and let's address that, and then can you go over the Lightning CLI? How does it track all the arguments?
So Lightning CLI is pretty new, and I haven't looked into the source code too much, but I suspect it does some meta programming. Basically, it will check the what is it called? The method signatures and doc strings for your Lightning module and your Lightning data module, and from there it passes out what are the inputs required and puts them into the help menu, which is pretty sweet, almost like magic.
Cool.
Yeah. All right. So switching gears a little bit into DVC. My data is currently sitting under the data folder over here. And as you can see, I have a bunch of PyTorch files for training and validation and tests of images as well as labels. When we use DVC, we want to, when we work with DVC, we would add these files into DVC, which would create a metadata file. If I were to open one of these files, it's taking a while to load, kind of strange. Okay, so when you add a file to DVC, it will create a corresponding DVC file that keeps track of the hash and metadata of that particular object. Then you would commit this DVC file into Git so that you now establish the history of the data with the particular commit in Git, right? Once you've done this, you can then very easily share your code with share not only your code but your data across your team members. Now that you define this, the next thing that's to do is to run training. But rather than run training like this, it'd be great if we can also capture the full context surrounding the commands that you use to train and output your model. And we can do so using DVC data pipelines. I will show you very quick. I've already configured data pipelines for this repo. So let me just quickly show you what they look like in our experiment here. So if I run DVC DAG, it will output the pipelines. And in our example, we have defined two steps in the pipeline. The first step is that we want to train our model. And once we've trained the model, we want to evaluate the model on the test set. And so you can see over here, DVC visualizes for you all the data inputs that goes into each step. And so should any of these data inputs change, you can very quickly hit, very quickly type DVC reproduce, and it will automatically figure out which steps in the pipeline that can be cached and which steps in the pipeline that should be run again to get the same output. Let's take a deeper dive into the DVC data pipeline themselves. So this is how it will look like. The dvc.yaml contains the full definition of the pipeline. It contains the exact arguments that we want to run again and again for the train stage, the data dependencies, as well as the source code dependencies, and the configs that we can tweak to train our model. In the train phase, we will have one output that is tracked within DVC, which is the checkpoint file. And then in the second step, we have pretty much the same thing. Perhaps the only thing that I like to draw your attention to is that what was once an output in train is now an input in the evaluation step. And by doing so, you're effectively chaining those two steps in the pipeline all together. Doing it this way, when something changes in train, automatically evaluation gets triggered after that as well. And finally, we save all our results into the test metrics, into a test metric folder that we can visualize. And so once you've done all that, all you got to do now is just hit, let me just make sure that my data is correct. Okay, I just got to hit DVC reproduce, and then you will figure out what needs to be done. In my case, all the data are the same, so nothing has changed. But we can very quickly check out what has the metrics for a particular training run. Yeah. Or maybe, let me think. Yeah, let's check out the metrics for our training run. So this is assuming that I've already trained a model, right? And so once the model is outputted, I save the result into a JSON file. And as we can see over here, the model seems to be performing, pretty well, right? For each of the class is giving about a 90-ish% accuracy. Oh, but for class 7 is doing pretty poorly. I wonder why, right? So let's just imagine that we are digging through the data. We're trying to figure out what's the reason for the poor performance for this class. And thankfully, Azin was pretty sharp and she was able to catch the bug. For some reason, labels have been incorrectly labeled. Some of the labels of class 7 have been incorrectly labeled, and she told me, okay, she fixed the data sets, and now we can try to rerun it again. And so to do that, all I have to do is very simply check out her branch. Let me just remove that file. I just got to check out her branch. And then, and just to show you that something has changed between our two branches, the MD5, so the hash for that, the training labels have been updated. So Azin has found some bug and she's updated the data files and committed them to DVC, which is awesome. Yeah, and then all I got to do is make sure that when I have the file, I can reproduce it. So now that I've updated my files, all I got to do is that if I want to check out the model that Azin has created, I just have to do DVC repro. That's it. I don't have to. All the context is really captured in DVC data pipelines after all, right? Oh, in this case, I have data. So let me just force rerun to show you what would happen. So if I hit DVC repro, it will, in my case, trigger a training run. And this is where we can see the power of PyTorch learning come in play. PyTorch learning, as you can see, uses all the CPUs that are available to load data. And very soon we'll see how all our GPUs will also light up as we are using all the GPUs to train a model concurrently. And this speeds up things super quickly. And to some of the questions, I very quickly, yes, we will be sharing, we can share the source code for this later in the presentation. Yeah. Yeah, so you can see how all the GPUs are running right now, and this allows us to train things extremely quickly. And the best part is we wouldn't have to worry about all the engineering hoops and challenges that we have to go through just to get it to this state. That is the beauty of PyTorch Lightning. All right, I'm a bit short on time, so I'll probably just skip the rest of this reproducible one. Yeah. Oh yeah, we also have profiling, as you can see over here. We can profile which steps take the amount of time that each step takes, right? All right, just gonna quickly terminate things because we're a bit short on time. Yeah, so now that we've reproduced the results thanks to the change that Azin has found in the label file, we can then visualize the metrics once again, and lo and behold, for class 7, we're getting a 98% accuracy, which is great. Awesome. So let me jump back. Let me jump back to the slides. So to summarize, we've shown a very simple example how you can take your code and make it and supercharge it using DVC and PyTorch Lightning. And by doing so, you get to use the same code to be run on different hardwares. You can perform multi-GPU training. You have a robust training and evaluation loop. Furthermore, you now have all your hyperparameters parameterized in the config file. This allows you to very easily and quickly change different things so that you can run multiple experiments in parallel, and also makes for easy reproducibility of your code. And that allows you to share your experiments with your team members more easily as well. So yeah, we've used some of these tools in our engagements with portfolio companies, and we've noticed that we can reduce the training time from, say, weeks down to days, which is pretty amazing. Now that we've mentioned all of this thing, the last step before we can hand it off to production is to containerize the application into a Docker file. And then I'll pass it on to Kyryl, who will show what we can do after we've packaged into a Docker file. All yours, Kyryl.
Yeah, thank you so much, Chris. And thank you, Azin, for introduction. So yeah, hello, everyone. My name is Kyryl, and I'm going to share screen. And can you see my slides?
Yes, Kyryl.
Okay, cool. Yeah, so I'm going to take it from here, and I'm going to cover the last step of the journey of machine learning model, and in particular, like productization of machine learning. So let's get back for 1 second to the model lifecycle. We already covered experimentation. So what we need to cover right now is training and validation, or like retraining of your model in production. Sometimes a step refers as a pipeline, then model deployment, and then model monitor. So let's go one by one of them and chat about it. So what about training or retraining of your model? So sometimes when you refer that you're going to deliver a model into production, it's even not the model itself, like the checkpoint, but the pipeline, the training pipeline. And the reason for this might be different. Maybe you need to retrain it once a day or once a month or with any other cadency. Maybe you cannot train with full production data in your environment and you need to deploy it to another cluster. Maybe you deliver the training pipeline to your client, and there's like a lot of possibilities. For some team, of course, it's just simple. You train your model, pick up by hand some checkpoint from your experimentation stage and say, okay, this is what I want to deploy. But it's generally good practice to wrap your training flow into some kind of pipeline and deliver the pipeline into production. So all artifacts you're going to use in your production, you're going to also produce from production environment. And usually people here use a lot of like frameworks with endings of flow, such as Airflow, Metaflow, something other flow. We're going to stick today with Kubernetes kubeflow pipelines framework for creating a retraining pipeline for our models. Right, so, okay, we have a retraining pipeline. It tests, it's produce nice artifacts for us, so we can then reuse them in our serving part. So what about serving? So after you get your artifacts, like models, it might be a different format, such as SoyNX or pure PyTorch model or some TensorFlow model. You need to wrap it into some kind of way, so it might be useful for a business, right? I guess the most common use cases are you wrap it into API, or you run it with the batch jobs. You might process requests in streaming, or you even might to deploy it on edge devices such as mobile phones, or even put it into like a web browser, right? So we're going to cover today only batch use case just for simplicity, but there's also like possibility to extend it to like full API and like serve real-time requests. Okay, so right now you have your training pipeline. You can produce artifacts in production environment. After that, you have your model deployment, right? You run batch jobs with it, or you run API, or you like process streaming, right? What's else left? So of course, there's like really nice things to have in production, especially is monitoring. And the issue with machine learning models is that the general monitoring, as it was in software engineering, is not enough, right? Of course, we need to monitor health, like uptime of our service, right? We need to monitor resources, CPU, memory, disk space, etc., right? But unfortunately, it's not enough. And the case is the next. If something's wrong with the service and can process requests, you're going to be notified about it, right? In the worst case, by your users, but somehow you're going to know it. But the bad part, the dark side of machine learning is that sometimes you can process requests completely normally. All uptime metrics will be fine, but something wrong with your model or with your data, right? Maybe data distribution changed it. Maybe some pandemic happens and patterns of behavior change, etc., like how people spend money or how people, I don't know, spend time at home, etc., etc. So this is one of the example, like data shift in your ML model lifecycle. Another one is very common is that you also need to make sure that the model performance is stayed the same. So apart from the data shift, you also really need to monitor the model performance and understand when you actually need to retrain to get the new data and retrain and get and deliver new models, updated models with the latest changes into production. So that's kind of what left in our model lifecycle journey. So we're going to cover today model training, retraining pipeline, batch inference, and data drift monitoring. And for our demo, we're going to use next step. We're going to cover several topics. So first one, we're going to cover how to manage infrastructure for everything, what we discussed. And for infrastructure, we're going to use AWS, Kubernetes, and kubeflow pipelines. So if you're not familiar with Kubernetes, there is no need to know it in deep, but very, very high level. It's just a way to orchestrate work with multiple machines. So you have a cluster with, I don't know, hundreds of thousands of machines, and you work with one entity with help of Kubernetes. This is the main idea. Kubeflow pipelines, it's kind of wrapper on top of Kubernetes, where you can communicate with your infrastructure on a much more high level way, other than working directly with Kubernetes. Because sometimes data science team might not need to know Kubernetes because this is not their responsibility. So they just work with kubeflow pipelines and follow kubeflow pipelines interface to work with infrastructure and own process end to end. And small remark, sometimes I'm going to say kubeflow, sometimes I'm going to say kubeflow pipelines. Usually I mean kubeflow pipelines when I say kubeflow. Of course, because kubeflow is like a big piece of software. There's like a lot of components, but we're going to cover only small part of it, kubeflow pipeline. In terms of the models, We're going to work today with two models. We're going to work with tabular model, just a simple XGBoost example, very dumb, very stupid example I put just for this demo. And another model, we're going to take Kreese model and going to run it on we're going to run training and inference. And our goal for today is basically have managed infrastructure. Then we want to build the retraining pipeline. Then we want to put the batch inference pipeline, and then we want to introduce some kind of monitoring for. And as I said, monitoring will be only about data sheet and data. So that's our plan for today. And before moving into the code, I would like to pause for 1 second and see if there is any questions I might address right now. Check. So I think that so I can do like two last questions. In this demo, we are training our model on OS GPUs. Yes, that's oh yeah, that's Chris. That's correct. And how we scale the training as a team. Yeah. So for the last question, it depends on from company to company, but one of the good pattern we use Kubernetes and Kubeflow pipelines, and this is what manage infrastructure for us. So this is how we scale. And we even have use cases and case studies when one of our portfolio company moved from SageMaker to Kubeflow pipelines just because SageMaker didn't fit them well. So they moved to Kubeflow pipelines. But yeah, we usually scale it with some kind of orchestration techniques. And in 90% of the cases, it's a Kubernetes-based orchestration technique. No, it's not big at all. It's not big at all. And I think we're going to cover this in a demo. I think I will answer this question more precise in demo, but it's no more than like 100 machine. Okay, cool. So, okay, if there's any questions, I can stop and answer them, but let's move to the demo part. The first part in the demo might be a little bit tough. It's going to be like infrastructure part. And if you're not working with infrastructure directly, bear with me for like 10 minutes. We get back to machine learning part short after. So first part of our demo is we want to run compute for us. We want to run some environment where we can serve our models, deliver them, and eventually at the end, we would like to get something like this. So this is the Kubeflow pipelines UI, where you can configure and run your training inference jobs and can spin up like some other like inference API servers with Seldom or kind of serve. But this is what we want to get at the end. So it's a Kubeflow pipelines UI. You can work with it via UI, via CLI, or via Python client. It has a couple of components. First component is that it's a pipeline itself, where you just define what you want to run. So this is like example, like open source example of some demo example of pipeline, which goes by default with pipeline, with Kubeflow pipeline installation. But it's basically just a graph of your operation. It might be like load data, run training, run inference, do something else, like in parallel if something fails. So it's very, very similar to Airflow, DAC, direct acyclic graph, or like any other like this tool. Another one, two important entities in Kubeflow pipelines is runs and recurrent runs. It's basically very simple. Just
sorry, Kyryl, I just wanted to see if you can zoom in a little bit before.
Yeah, sure, of course. Is it better now?
Yeah, I think this is great. Thank you. Okay,
cool. So again, pipelines is just a definition of what we want to run. Run is actually like execution of pipeline. Recurrent run is run pipeline every 1 minute, every 2 minutes, every like third month, or like whatever you want to run, right? Then you have your experiments, which is basically a way to group your pipelines. And then you have artifacts, which Kubeflow check all artifacts which goes into your pipeline or go out of your pipeline. And we're going to work with each of those components into more details in the next stage after we finish with infrastructure. But this is our kind of end goal. just have this tool, Kubeflow pipelines, which is going to do for us 4 main functionality. It's going to manage compute for us. It's going to manage storage. It's going to be scheduled for us. So basically, it's going to, like, instead of us running everything like every day, it's going to do this for us. And you're just going to define like cron expression when to run it. And it's going to be a metadata storage for us. So basically those 4 components: compute, storage, metadata, schedule. And this is our like end goal with this infrastructure exercise. So how we from nothing going to arrive to this stuff. So we start with we are using AWS SDK for this. So let me switch into my VS Code. So what we're going to install, we're going to create Kubernetes cluster, which is called EKS. It's a Kubernetes cluster in AWS. Then we're going to install Kubeflow pipelines there. After that, we're going to create cluster after scaling. So we don't want to spend time on GPU nodes or like expensive CPU nodes, right? We want to scale up and scale down them when we use them and when we don't use them. For example, if we run like, I don't know, 1,000 different trainings, right? It's going to be peak. So we're going to scale up for like 100 machines. And then if there is nothing happens, we're going to scale down to like our default small amount of machines. Right? We're also going to install some NVIDIA drivers to run GPU workloads and some CI/CD just to use Docker. So to work with this tool, you need to install AWS SDK. It's basically the way to code your infrastructure in pure Python. So instead of going into EKS cluster and create instances like launch instance, etc., you're going to code everything in Python, what I want to get. Once you install it, you export your AWS key with which you want to work. And after that, I can just switch into, let me scroll down, into our infrastructure component, and it looks like this. So we have our application, which basically just extend the base class from AWS SDK and says, okay, I would like to create machine learning infrastructure step. And I would like to create EKS cluster. I would like to create Kubeflow pipelines on top of this. And I would like to create NVIDIA drivers on top of this. Let's go into EKS cluster. What's inside? So inside, we in Python just type, okay, please create EKS cluster for me with this name, with this Kubernetes version. And I don't want any capacity, default capacity for it. And after that, you create 3 workflows. So first one is Kubeflow nodes. Those like cheap, small, and expensive nodes, which always running, and where you scheduled all your like system workloads. Like for example, this UI is running there. Basically, everything that's not expensive, not machine learning related, you schedule to those nodes. And after that, you created 2 different node pool. One is for CPU intensive workflow. Let's say if you train a lot of XGBoost or a lot of scalar models, right? You don't need GPU, or you run a bunch of inference APIs, which you also don't want to use GPU. You want to use GPU only for your training. You might redirect all your CPU intensive workload to those nodes. And here I would say, okay, please give me this type of nodes. And by default, I'm going to use 0 nodes. And the max size is 3 nodes. And after that, the same story with the GPU nodes. If I need GPU, I going to scale up this node pool. And then you enable after scaling for each of those nodes or those node pool in your Python code. So that's how you set up your EKS cluster, right? And after that, you run Kubeflow pipelines on top of this. And because Kubeflow pipelines is it's nothing other than just a Kubernetes YAML definition, we just apply from official website of Kubeflow, just those YAML definition where like list all our resources and create Kubeflow pipeline deployment on top of our Kubernetes cluster. So again, we have our SDK, then we create our EKS cluster with after scaling, and on top of this, we run our Kubeflow pipelines. So this is how the main idea how it works. And at the end, when you deploy this and this command, this SDK, how to deploy it, basically just type SDK deploy. Basically, I'm mostly using those 3 commands for this. I'm using SDK deploy when I actually create the deployment of my infrastructure stack, SDK diff when I want to change something in my infrastructure. Let's say I would like to update default size of this node, or I would like to get one more of those, but I would say with 4 GPs, right, etc. And then I might run destroy, for example, after this demo, because it's like a demo deployment, I'm going to destroy it. And eventually, when you run it, here in CloudFormation, we have our stack deployed. Everything is tracked, everything in code, so like you are not going to lose any infrastructure resources. And this is our EKS cluster deployed yesterday, just because the whole deployment takes like around 40 minutes. So I run it before just to run demo more smoothly. And this is our 3 node pools. I will scale up it for 1 machine just before demo, so we are not going to wait for machine to scale up. So for our pipelines. So that's basically how we manage the infrastructure. When this SDK deploy finished, what we get as the output, we get first the command to set up our kubectl client. And again, if you're not working with Kubernetes directly, you don't need it, but I'm using it for tracking state of my cluster. And I'm using a tool called K9S, where I basically see all my pods running up. So you see that I have like my kube system pods and also my kubeflow pipelines, where I see some like pods for ML pipeline itself, but also all pods all training we're going to create also will be like a different pods here. But again, if you're not into infrastructure, you might completely ignore this. What's interesting for you is basically those 2 URLs. First one is for kubeflow pipelines, where you just can create your pipeline, and another one is for Minio, which is basically the way how kubeflow store everything. It might be a wrapper on top of S3 or just like file system. It's basically just like you can think about it as a file browser for all your artifacts and all your files. So that's how we manage the infra. And before move to ML part again, to our tabular example, I want to stop and see if there is any questions.
Kyryl, I think there were 2 questions. The first one was about this package, Polomi, and they were asking whether you're using it in the demo or if you're using something else.
So Polomi. Not sure I know about this package. AWS SDK. So I can answer like the last question. As you see, first time I see an AWS SDK. So SDK, I'm guessing AWS is used by default. Yes, that's correct. So AWS SDK is, yeah, thanks for clarification. So AWS SDK, yes, it's only for AWS. You cannot use it with other cloud providers. I guess the closest analogy to it, it's Terraform Python SDK. I guess they release it shortly, where like it's same idea. You just also, instead of AWS SDK, you use CDK FT CLI, and the same idea. You also code your infrastructure as a programming language. That's kind of it. So you see, even like the idea is kind of similar. The syntax is very, very similar. And it's much more high level than Terraform and CloudFormation. And it's like, yeah, just way to code your infrastructure as like a programming language. The only downside of it is that it's written in Node.js and it's just translated in Python. So sometimes when something goes wrong and you need to read source code, it might be challenging.
And there is another question. Have you considered using the library Cortex to abstract all the infrastructure work of setting up the Kubernetes cluster? If not, why someone would use Kubeflow versus Cortex?
That's a nice question. So we used Cortex for some another project, but personally, I use it way before it is. So like, I don't know which kind of like version I used. I used it like around like 1 year ago when it was completely different product, and where it was more like an inference server where you like define, okay, this is my Python file, this is my requirements.txt, this is my model file, please serve it for me, right? And right now it's more like a serverless way to like serve like any Docker images, and you need to write your own fast API services. So I would say the difference, at least as I know, at least like, because again, I used Cortex 1 year ago, and right now I'm only read the documentation, but don't have a lot of hands-on experience. That yeah, they both rely on Kubernetes, and sometimes you want to, if you want to work with Kubernetes directly, and you want to have like a more like a control on it, you might use AWS SDK. With Cortex, you kind of like just outsource a lot of this stuff to Cortex CI, which might be good for a start, but eventually you want, for example, for ClickUp, we're working with this stuff. It's important for them to have like audit of all their infrastructure and code it in one way. So like from one team to another, it's going to be like a similar pattern. In terms of the inference models for Cortex, so I don't know, I haven't tried it for a while, but I know that Seldom and Kasurf kind of might be replacement for it, a little bit more easier, where you don't need to write your own like web server. You can just provide the your path to your checkpoint, and it's going to serve it. So I know, I think it depends on the use case, and they might even cover like different use cases, because Kubeflow pipelines, it's more for like a retraining and batch inference, and it needs something extra for API, while Cortex is more for API, for different kind of APIs, like asynchronous API. I know that it has task support, but I haven't deep dive into this a lot. Okay, so
I think there is no more question for now. Maybe
okay,
we can
cool.
continue and keep the questions for
Okay.
the last part.
Sure. Cool. So, okay, now we have our infrastructure, right? We set up our infrastructure. We have those two nice tools. Mostly going to work with this pipelines. So let's create some pipelines, and actually let's create some server for all. So let me get back, and let me go into our tabular example. So let me scroll this down. Okay, so tabular example, it's like the dumbest example possible. I wrote it just for this demo. Very simple, just to showcase the way how to work with Kubeflow pipelines. And usually we structure our project in the next way. We have actually like a package, Python package, where like all code is scripted. Then we have our test for this package, our notebooks, and then our pipelines where we list how we're going to structure this for Kubeflow. So first part is the package itself. And I think this is quite simple. If you either work with some machine learning model, you kind of might create similar setup where we just, let me just very briefly show you inside of the Docker image that we have. Let me scroll it down, and the first operation, we can just load data, and it's going to create some kind of data set for us, right? If we go inside here, it's just basically just load Boston and save it there, right? We might think, okay, this operation going to load some data from a Snowflake for us, right? Then we run preprocessing, which just going to split this data to training, validation, and run some feature engineering. And again, feature engineering here, I just took it from my head. I just like took some random polynomial features and apply them. I didn't think that they need it, but just like as a showcase. And then you run your training model and produce some XGBoost model and get some mean square error. Right, and after that, you might run inference for this and produce some predictions, right? Oops, sorry. Yeah. So that's like a very, very straightforward way to work with ML models. So let's move it into Kubeflow, how it might look as a pipeline. So the first step is just to package it into Docker. So we have a Docker file, which is pretty straightforward, and then we build it and push as an image into our container registry. But now I think this is it. So I think I updated it lately. And after that, we define our pipeline. So what does it mean to define a Kubeflow pipeline? So basically, we work with KFP package, which looks like this. We create a client for Kubernetes, for Kubeflow pipelines. And this client just take host and maybe some authorization, but I didn't create any authorization for this demo. And after that, you define your pipeline with this decorator. So it's basically DSL. It's kind of like domain specific language for Kubeflow, where you just define what your pipeline looks like. And right here, it looks very, if I'm going to open README, close to here, you, oh yeah, it's too small, I guess, to open README. So if I open a README on one side and pipeline another side, you're going to see that here we load the data. So same here, we just say, please, could you run this command, load data, save it right here, and take this file as output. After that, we run the training preprocessing. Same here, we run the training preprocessing on this data, and we produce those 3 files. And same here, we just say, please, this is your input, and you're going to take it from previous stage and put it right here. And this is your output. It's going to be training dataset, validation, and feature engineering. And so on, so on, so on. You basically construct what's the input, what's the output for each of your pipeline. So let me just create this pipeline. So to create it, I specify pipelines, KFP pipeline, and then I just copy paste this endpoint, but with name pipeline. Okay, so yeah, I think we have some error here, but it's because I not commented the string. So let me create again. It's okay, we created a pipeline. It looks like this, called tabular model. You see, so I run it twice because the first time I get this error because of syntaxes. So I create 2 versions. Because every time you, because every time right here it defines that I took my function, I compile it into YAML file, and if there's already exists pipeline, I just upload a new version of the pipeline. If there doesn't exist, I create a new pipeline. So this is how pipeline looks like. It's basically just a visual representation of what you code there. Your command, your image, where you're going to run, your command, your image, etc., etc. So let's run it. Again, we can run it from Python, we can run it from UI or from CLI. Let's do it from UI. So I select some kind, let's select default experiments. So like we usually follow like 1 experiment for 1 model. And we're going to start. And right here, we can track the execution. We can see some metadata, what we expect as the output, what some details of this operation, obviously, so it's done. So we can actually go into each of these artifacts and see where it's going to be used, who the producer of this artifact, etc. We can actually see the logs. I think we don't have any logs here, but we might have it in a train model, yeah. And the nice part, we also see the pod, because under the hood, it's run inside of the pod. So you see, this is, I think it's somewhere down. Yeah, so this is like a 3 pods just executed with this tabular model. You see like 37, 2 seconds ago. And this is like how we moved from, okay, we have our code, we package into Docker file, then we drop into the pipeline, and then we create a pipeline in Kubeflow UI. Right? So this is our training pipeline. Let's add some monitoring into it. So for example, if you want to run, if you want to see, let's imagine that this pipeline is repeated over time, right? And here we produce training and validation data. Let's see if there is any like a distribution shift over it. So let me again just create a pipeline. So we see that I defined the old pipeline I created here, and I upload the new version of the pipeline. So if I go into my pipeline, you see that after training purpose, I have like a 2 additional operation. The first one going to detect drift with library called seldom alibi. Another one going to use library called evidently. They both kind of doing same things, where like alibi just create, like just run 2 statistical tests, and third one test is actually learnable model. So it's actually a trained model to detect the distribution of your data, and then you have actual model and plus another auxiliary model which is going to tell you, okay, is this like in your distribution or not? And this model, evidently it's just a really statistical test, bunch of statistical tests, but they have really nice visualization. So let me just run this pipeline. And again, I'm going to assign it to this and start. And yeah, you see that the version here is different. I can go and see that I run this version. And I think it should be done quite fast because all previous steps should be taken from cache. Yeah, you see that it's actually not running because it's taken from cache. Yeah, let's give it some time to run. And after that, let's say if we want to add our inference, again, it might be a different pipeline. I prefer to keep it like just for simplicity as a one pipeline. But let's say we add inference, and then after inference, we even want to detect data drift of the, but was already prediction. And let me create a new pipeline. So what's happened with this one? Okay, so this one is still running. We have 2 operations, so those one taken from cache, and this one is still running. I think we can go into pod definition and see what's happening with this pod, and it should somewhere here. Yeah, so you see there's like a 2 pod. So this pod is still only like creating. So meanwhile, let's go into our pipeline again. So again, this was the original version. Then I added 2 anomaly detections, 2 data drift detection for training and inference data. Let's think that our validation set our inference data at the same time. And then I added inference and anomaly and drift detection for inference. So let me go back to runs. Okay, so this one I think still running. So let's give it time and run our latest pipeline. Okay, so okay, while it's running, let's give it some time and get to wrapping up Kyryl model from this repo from Nissan DVC. But before this, let me stop for questions. Okay, so are there things to do the cost reduce this issue specific package because of cost benefits? So you mean infrastructure cost or time cost? I guess the 2 main considerations we take care when we choose packages or like approach is how we're going to pay for compute and how pleasant and how easy to work with this package. That's the main consideration while we choose like legacy cost too. For example, there was like a really clear concern with Kubeflow is that should we use Kubeflow, which is open source and has not ideal documentation and not ideal source code, or should we just use some managed service, right? And there's like always this trade-off. So far, we're moving with use Kubeflow and relying on open source. Maybe like spending a little bit more time on like maintenance this, but so far it's not a huge cost for us. If it's going to take even more time, that's really nice. If it's going to like cause more problems for maintenance, we're going to reconsider this. That's a partial reason why we keep everything kind of kubeflow agnostic. So we use Docker, and our pipeline can be run anywhere. So kubeflow is really nice, kind of like orchestrator, but there is not a big issue to rewrite this into Airflow. I mean, it's not a like impossible task to write it in Airflow. Of course, it's going to be like costly, but still, because it's like all Docker and all clear contract, we kind of save from this side. So let me check if this is done or not. Okay, cool. So our 2 runs is done. So let's take a look into them. If they set, okay, so we run the drift detection for Alibi. And again, small comment about drift detection here. I, for purpose, introduce some distribution change. So even if you read the same file, I on purpose corrupt the second file, I min-max scale it. So for anything, you're going to get the different distribution. Of course, if your file already not done. But because our file, like they're like any kind of files, we're always going to get this data set drift detection. So right here, I can check. Let me try to refresh this. I think it's stuck for some reason. Yeah, sometimes it's quite slow, or it's my internet connection. So yeah, you see that here I detect drift with all 4 methods, and with evidently I even have some kind of visualization here. So here I even put like a visual representation of drift. So if I click here, I'm going to see features by features, what's exactly happening, why there is like a drift, and what is like a data distribution, how it was changed. And the same with inference. So here we train model, and this is our prediction output. We of course can view them all, and right here we can see this is like alibi detection. So it's going to be like only like console output, and here evidently prediction. So we're going to have even like a visualization here, but it's only one feature here. Okay, so that's with tabular model. So let's very quickly go over the Chris model. And for this, basically what you need to do with this repo, which is from Chris, I just create my config for experimentation and my config for prediction, and just put a simple pipeline here. And of course I put it as a wrap it into Docker, save it on our Artifactory, our image registry. This is how it looks like. Yep. And then define a simple pipeline. Please use this Docker image, and first operation is train, and please run DVC pull, run DVC repo. This is your output, metric, checkpoint, and test images. And please use GPU. So I said like limit GPU is 1. And because we pull data from this tree, I also specify AWS secrets. So we were able to work with this tree. And then let's me also like increment predict that after that, I pass checkpoint and test images as an input to this container and run prediction. So let me switch to this repo and run KFP pipeline on this. So let me just select this one, and here I'm going to type pipeline. Okay, so here we go. This is our pipeline, train model, predict, and let me create a simple run from it. Let me assign it to default, and then start. And the same, the first operation going to be really fast because I already ran it. And sorry, I think I assigned it to one. So this one, what I ran before, this is a train operation of this model, and the output is very, very similar to what Chris had. And we store all logs, and this was run on the GPU, and GPU was scaled up automatically. And to run inference, so you see that it takes this output from the cache, And this operation is running right now. So yeah, this is kind of how we run and how we can wrap model which we already have with PyTorch-like and into Kubeflow pipeline. Cool. So I think I will stop here and we'll answer any questions I have.
Maybe while we're waiting for questions, a tiny note. If you're interested in the existing opportunities, please check our career page on our website. We have a lot of different open positions at Georgian, including a full-time position for machine learning engineering. Yeah, I will share the link in the chat. Very good.
So I see the question, can you share some performance benchmarks? Performance benchmarks of models or the stack itself or the productivity? Because I can briefly talk about MLOP stack benchmark performance benchmarks, and we measure it basically time to production. How much time goes from the stage of your experimentation when you say, okay, this model is not perfect but good enough for me to deliver into production, to actually like production system where like business can use it. It depends on the technical depth, on the MLOP workflow of the company, but usually with Kubeflow, what I showed today, it's usually days. So first model for like someone who not worked with this, it might like weeks. I guess the longest was with Kubeflow was like 4 weeks, but right now it's like days, under like 1 day. Data science team without any engineering support can put models into production by just using this abstraction. And this counts for like, I don't know, 80-90% of the models. For some exotic use case, yes, of course, like team supports Kubeflow, need to interfere, like, okay, we need another compute, or we need new type of GPU because we don't keep the LSL or something like this. With other MLOP stacks, it's also like varies. I think that is pretty much all from me about the coding part, and then I pass it to you.
Great. So I think we're coming to the end of our workshop today. Thank you everyone for joining, and we hope that you know how to open an efficient bakery at this point. So with having said that, I just wanted to reiterate over the job opportunities at Georgian. If you're interested in this, like in any position, including our machine learning engineering position, please feel free to reach out to any of us on LinkedIn. And I shared the link to our machine learning community where we run and host these sort of sessions on a monthly basis. If you're interested, please register by the link that I shared in the chat. And with that, I think our workshop comes to an end. Have a great rest of the day, everyone. And yeah, thanks for attending our workshop again.